The bombardier's hands trembled, not from fear, from cold. 23,000 feet above Nazi Germany, the air bit through leather gloves, through wool, through skin. Minus 40 degrees Fahrenheit turned breath to ice crystals that fogged the eyepiece of the most secret weapon in the American arsenal. It was October 14, 1943. Below, the city of Schweinfurt waited. Its ball-bearing factories, producing 60% of Germany's entire supply, represented a single point of failure in Hitler's war machine. Destroy them, the generals promised, and the Third Reich would grind to a halt within 4 months. The bombardier pressed his eye to the rubber cup. Through crosshairs, he watched the target slide into view. For this moment, he'd been trained in absolute secrecy, sworn an oath, told the device between his legs was worth more than his life. The Norden bombsight, a mechanical analog computer capable of calculating wind drift, airspeed, altitude, and bomb trajectory in real time. From 6 miles up, they said it could drop a bomb into a pickle barrel. Today, 60 B-17s would never return home. 600 men, 20% of the attacking force. But the bombardier didn't know that yet. What he knew? This machine cost more than a house, weighed 50 pounds, contained 2 gyroscopes spinning at 7,800 revolutions per minute. When he clutched in the autopilot, the Norden would fly the bomber itself, his pilot reduced to a passenger for the final 3 minutes. The factory complex filled his view. Metal bands connected to the aircraft's controls. Gears meshed, motors hummed. The bombsight did what no human could. It thought ahead. It calculated where a falling object would be, not where it was. Outside, Messerschmitt fighters closed in. Inside, the Norden's mechanical brain solved equations pilots couldn't begin to understand. The release point indicator slid toward the aiming mark. Stay with this story, because what happened next would change everything America believed about precision bombing. The story began 20 years earlier in a cramped apartment in New York City. Carl Norden, a Dutch engineer educated in Zurich, bent over his drafting table. It was 1920. The Navy had a problem. Bombs dropped from aircraft scattered across hundreds of yards. Wind, altitude, speed, every variable conspired against accuracy. Norden had worked with Elmer Sperry on ship gyrostabilizers. He understood motion, understood precision, but this was different. A falling bomb traveled at 350 feet per second. At 20,000 feet altitude, it fell for nearly 40 seconds. In that time, wind could push it a quarter mile off target. The aircraft kept moving. The Earth rotated beneath. The mathematics alone defeated most bombardiers. By 1927, Norden delivered his first prototype to the Navy. It wasn't just a sight, it was an analog computer. 2 DC-powered gyroscopes spinning in opposite directions, maintaining absolute vertical reference regardless of the aircraft's pitch or roll. The device measured ground speed directly by tracking landmarks, eliminating guesswork. It calculated the bomb's trajectory continuously, adjusting for every shift in wind or altitude. In 1931, the Mark X-15 arrived. Tests at the Navy Proving Grounds in Virginia showed results that seemed impossible. A circular aeroprobable of just 75 feet from 21,000 feet altitude. 75 feet. From 4 miles up. The Army Air Corps noticed. In 1932, they purchased their first units, designating them the M Series. By 1934, American strategic doctrine crystallized around a single concept: daylight precision bombing of specific industrial targets. No more carpet bombing cities. No more night raids scattering explosives across neighborhoods. America would strike with surgical precision. The Norden became classified above top secret. Production ramped up at Carl L. Norden, Inc. in Brooklyn. The company would eventually produce over 50,000 units at a cost exceeding $1 billion, the same budget as the Manhattan Project. But there was a problem no one anticipated. What worked flawlessly in the clear skies of Virginia would face a very different test over the smoke, flak, and terror of the Third Reich. The machine emerged from obsession. Norden worked in Switzerland when he could, at his drafting board in New York when he couldn't. His business partner, Theodore Barth, assembled prototypes in his apartment, precision components spread across kitchen tables. The first challenge, keeping the sight pointed straight down while the aircraft banked, pitched, and yawed. Solution, a gyroscopic stabilization platform. 2 gyroscopes mounted perpendicular to each other. One for vertical orientation, one for azimuth reference. Both spinning at 7,800 revolutions per minute, powered by DC motors the size of cigarette packs. But gyroscopes drifted. Every mission, bombardiers spent 20 minutes righting the platform, comparing its attitude to spirit levels viewed through a glass window. Time-consuming, vulnerable to error. In combat, 20 minutes felt like 20 hours. The second challenge, calculating where a bomb would land when wind, altitude, and airspeed changed constantly. Earlier bomb sites used the wind triangle method. Bombardiers performed slide rule calculations before the bomb run. By the time they finished, conditions had changed. Norden's innovation, measure ground speed directly. The bombardier aimed the telescope at a landmark, tracked it, timed how long it took to travel a set distance. The Norden's mechanical brain, cam-driven linkages, differential gears, integrators, converted this into trajectory solutions in real time. A clockwork mechanism with vibrating reed synchronized bomb release. The third challenge, keeping the aircraft steady during the final approach. Human pilots couldn't maintain the precision the bombsight required. Hand tremors, overcorrections, fear. Between 1932 and 1938, Norden developed the Stabilized Bombing Approach Equipment, the SBAE. Not quite an autopilot, something stranger. Metal bands connected the bombsight to the aircraft's rudder and ailerons. During the bomb run, the Norden flew the plane. The pilot became a passenger, hands off the controls, watching his bomber obey a machine's commands. In the factory workshops in Brooklyn, technicians assembled devices requiring tolerances tighter than a Swiss watch. Every component had to function at -40 degrees Fahrenheit, at 25,000 feet, while being shot at. The question wasn't whether it would work in a laboratory. The question was whether flesh and metal could survive long enough to use it. August 17, 1943. First light over England. Lieutenant Byrne Lay Jr. climbed into his B-17 as an observer on the Regensburg raid. He'd never seen combat. He was about to see too much. The mission plan looked elegant on paper. 376 bombers in 2 waves. The first would hit Messerschmitt factories at Regensburg, then continue to North Africa. The second would strike Schweinfurt's ball bearing plants 30 minutes later, catching German fighters on the ground refueling. Fog delayed the second wave. The gap stretched to hours. Over Belgium, P-47 Thunderbolt escorts reached their fuel limit and turned back. The bombers continued alone into Germany. At 12 o'clock level, the intercom crackled, Messerschmitt Bf-109s flying head-on, a new tactic. They'd learned the B-17's nose guns were weakest. John Comer, flight engineer in the top turret of a 381st Bomb Group Fortress, watched the sky fill with fighters. It looked like the entire Luftwaffe was lined up. Cannon shells, 20mm Oerlikon rounds, punched through aluminum skin like paper. Then came the Norden's moment. Bombardiers across the formation clutched in their autopilots. For 3 minutes, they flew the aircraft by proxy. Crosshairs centered on factory roofs. Drift knobs adjusted. The mechanical computers solve their equations. Bombs away. Post-strike photographs show devastating accuracy. The 40th Bomb Group dropped 53% of bombs within 1,000 feet of aim point. Direct hits on assembly buildings. Albert Speer, Germany's armaments minister, reported an immediate 34% drop in ball bearing production. The cost, 60 B-17s, 600 men, 20% losses. In Virginia test ranges, the Norden achieved 75-foot accuracy. Over Schweinfurt, under combat conditions, the average circular error exceeded 1,200 feet. The bombardiers had done everything right. The Norden had worked exactly as designed. But combat wasn't a test range, and Germany wasn't finished fighting back. In Berlin, the raid triggered panic. Speer convened emergency meetings. Ball bearings were everywhere: tank treads, aircraft engines, gun turrets, U-boat propeller shafts. Lose Schweinfurt's output and the entire war machine seized up within 4 months. Or so American intelligence believed. In Washington, General Hap Arnold studied reconnaissance photos. The Norden had proven itself. Now they needed to prove American daylight doctrine could win wars. The British disagreed. Air Chief Marshal Arthur Harris commanded RAF Bomber Command. He'd watched his crews try daylight raids in 1940. The Luftwaffe had slaughtered them. Now the RAF bombed at night, area bombing, saturating entire city blocks. Harris called the American approach panacea targets. Precision bombing was fantasy. The weather over Germany was overcast 300 days a year. But Arnold had the Norden, and he had production numbers the British couldn't match. By March 1944, the 8th Air Force's average daily operational strength reached 974 heavy bombers, double the number from 1943. The Germans adapted. They dispersed ball bearing production across dozens of smaller facilities, stockpiled reserves, imported bearings from Sweden, Switzerland, Italy. Schweinfurt's factories, damaged but not destroyed, resumed operations within weeks. Intelligence officers discovered something unsettling. Germany had never been close to a ball bearing shortage. They'd had enormous surplus capacity all along. September 1943 production exceeded August, before the raid. The Norden's precision was real. The strategic intelligence was wrong. But the device had become more than a weapon. It had become doctrine, justification, political capital. In England, bomber groups received new orders. Return to Schweinfurt. Finish the job. Mission planners scheduled October 14, 1943. They called it a maximum effort raid. 292 bombers. The entire striking power of the 8th Air Force committed to a single target. The crews called it something else. They called it suicide. Because this time they knew what waited for them over Germany. And this time the Luftwaffe would be ready. Thomas Therian crouched at his waist gun as his B-17 crossed into German airspace. 9:45 hours, October 14, Black Thursday. The Norden sat 20 feet forward in the bombardier's position. Therian couldn't see it, couldn't hear its motors humming, but he knew it was there, the reason they were flying into this hell. Bogies, 10 o'clock high. Crimson tracers arced across the sky. Therian squeezed his .5 caliber trigger, 800 rounds per minute hammering into his shoulder. A Messerschmitt rolled past, so close he saw the pilot's face. Then the sound, not the rattle of his own gun, something else. Cannon fire. The B-17's thin aluminum skin disintegrated. The intercom died. Blood sprayed across the fuselage interior, his fellow waist gunner, Loren Fink, clutching his chest. Therian dragged him toward the escape hatch. 200 yards ahead, the lead bombardier activated his Norden. The autopilot clutched in. The formation flew straight and level, sitting ducks for the flak batteries below. Black clouds of shrapnel burst around them. 88mm shells, 16,000 rounds fired to bring down a single bomber. The sound of metal hitting metal, pinging, tearing, screaming. Inside the lead ship, the bombardier watched his target through the eyepiece. His hands moved across the controls, right hand only, because the left held him braced above the telescope. The Norden could only adjust vertical or horizontal aim at one time, not both. In combat, this mattered. Drift knob, range crank, the mechanical computer recalculated with each adjustment. The release point indicator slid toward the aim point. 3 minutes felt like 3 hours. Bombs away! 292 B-17s pickled their loads. 4,000 bombs tumbled toward Schweinfurt. Therian felt his aircraft lurch. Then someone grabbed him. "We're bailing out!" He pushed Fink through the door, helped the wounded radio operator. The plane lurched again, cannon fire. He lost his footing. When he looked up, he was alone in the disintegrating fuselage. The Norden was still calculating trajectories in the nose section, but the crew was gone. The Norden bomb sight consisted of 2 primary assemblies: the sight head, nicknamed the football, and the stabilizer. The sight head contained the analog computer, cam-driven linkages, differential gears, integrators processing variables, altitude, airspeed, drift, temperature, air density. Inside, a mechanical clockwork with vibrating reed and timing disc. When calculations reached release point, a solenoid tripped, automatically, no human decision required. The gyroscopic platform maintained absolute vertical reference. 2 gyroscopes mounted perpendicular, one for pitch, one for yaw. Spinning at 7,800 RPM. Ball bearings manufactured to tolerances of 0.001 inches. Ironically, the device designed to destroy ball bearing factories required the most precise ball bearings ever made. The stabilizer housed the directional gyro, the azimuth reference. Metal bands connected through pulleys to the aircraft's autopilot. During the bomb run, the Norden commanded: turn left 2 degrees, climb 50 feet, hold heading 287. The SBAE system, Stabilized Bombing Approach Equipment, translated these commands into servo movements. The aircraft obeyed. But the system had vulnerabilities. Vibration from engines could flat-spot gyro bearings. A hard landing required complete overhaul. Carbon brushes from DC motors spread dust into sensitive mechanisms. Temperature extremes at altitude caused metal components to contract differently. Lubricants froze solid. Rubber eyepieces became brittle. In late 1944, technical reports showed 75% of some bombsight batches fell out of specification, missing targets by 280 feet from 20,000 feet when specs called for 50 feet. The claimed precision, hitting a 100-foot circle from 21,000 feet, was achieved under perfect conditions: test ranges, no enemy action, experienced bombardiers, optimal weather. Combat introduced chaos. Turbulence during bomb runs, evasive action, fear, fatigue, oxygen deprivation at altitude affecting judgment. The Norden calculated trajectories assuming steady flight, but steady flight meant exposure to flak. Some sources indicate the device was mechanical genius. Others suggest it was strategic delusion. Both were true. The question wasn't whether the Norden could achieve precision. The question was whether anyone could survive long enough to use it properly. The bombardier's oath was absolute: protect the Norden with your life. Before every mission, 2 armed servicemen carried the device to the aircraft in a canvas cover. The cover remained on until airborne. After landing, the bombardier deposited the sight in a secure vault, the bomb vault, under guard. Captured bombardiers faced interrogation about the device. Some carried thermite charges to melt the Norden into slag if capture seemed imminent. But the psychological weight went deeper than security protocols. Lieutenant Colonel Bjorn Lay Jr., observer on Rendsburg, described the carnage. Disintegrating aircraft were commonplace. 60 parachutes in the air at one time, hardly worth a second look. My brain turned numb to the death and destruction. The average B-17 survived 11 missions in late 1943. 11. Crews were required to complete 25 before rotating home. The mathematics were clear. Most wouldn't make it. They called it operational fatigue, the medical term for watching friends burn alive at 25,000 feet. Waist gunner John Comer remembered the cold, the fear, the impossible decisions during 3-minute bomb runs while fighters attacked and flak exploded. In those 3 minutes, the Norden flew the plane. The crew just tried to stay alive. Some bombardiers developed superstitions around the device, touching it for luck, talking to it. One claimed his Norden had personality. It liked certain altitudes better than others. Shell shock manifested in trembling hands, the same hands that had to make micro-adjustments to drift knobs while the aircraft bucked and shells exploded. A 1944 psychological study found bombardiers experienced unique trauma. They watched their bombs fall, watched the explosions, knew, unlike pilots or gunners, exactly what they'd done. The Norden promised clean war, surgical strikes, precision without civilian casualties. The reality was thousands of tons of high explosives scattered across error circles measuring hundreds of feet. Carl Norden, a devout Christian, believed his device would reduce suffering. No one told him the truth about what it actually accomplished over Europe. Not until after the war. The Germans had the plan since 1938. Hermann Long, engineer at Carl L. Norden Inc., was a proper German immigrant. He'd worked on early prototypes, understood the mechanisms. In 1938, Long delivered complete specifications to German intelligence, then vacationed in Germany, where he explained the device's operation in person. The Abwehr studied the plans, concluded the Norden wasn't practical for Luftwaffe purposes. German bombers flew lower, faster, in different tactical roles. But they understood what it meant for defense. By 1943, the Luftwaffe had captured multiple Norden units from crashed B-17s. Specialized recovery teams analyzed them, tested them, reverse-engineered components. The Germans developed their own solution, the Lot-Föhn-Rohr 7. Similar gyroscopic principles, different implementation, simpler to manufacture. More importantly, they adapted tactics. Instead of trying to match American technology, they exploited its limitations. The Norden required 3 minutes of straight level flight. German fighter pilots learned, attack during those 3 minutes. The bombers couldn't evade. The formation had to hold position. Flak batteries created boxes of explosive shells, predetermined zones the bombers had to fly through. At 25,000 feet, flak accuracy decreased, but forcing bombers higher decreased Norden accuracy more. German industry dispersed. Schweinfurt's ball bearing production spread across 60 smaller facilities, underground factories, captured plants in occupied territories. Sweden and Switzerland, neutral nations, supplied bearings throughout the war. Intelligence officers discovered post-war, Germany never came close to a bearing shortage. Enormous stockpiles existed. The bottleneck was myth. Albert Speer, interrogated after Germany's surrender, admitted the Schweinfurt raid's main flaw, not following up immediately. The first strike caused panic, but without sustained pressure, production recovered within weeks. American tactical evolution, the combat box formation, staggered bomber groups providing overlapping defensive fire, the lead bomber technique. One experienced bombardier in the formation, others dropped on his signal. Area bombing through clouds using radar, H-2X systems. Accuracy plummeted to 5% within 1,000 feet of target. By fall 1944, only 7% of 8th Air Force bombs hit within 1,000 feet of aim point. The Norden's promise, precision warfare. The reality, the need for long-range fighter escorts. P-51 Mustangs arriving December 1943 changed the war. Not the bombsight, the fighters.
August 6, 1945. The Enola Gay, a B-29 superfortress, climbed toward 31,000 feet. In the bombardier's position, Major Thomas Farabee. In front of him, Norden bombsight, serial number Victor 4120. The target, Hiroshima. Farabee activated the Norden, acquired the IOE bridge, his aiming point. The mechanical computer began its calculations one final time. At 0815 hours local time, the bomb bay doors opened. Little Boy fell for 43 seconds. The Norden's calculations put impact 800 feet from the intended aim point. For an atomic bomb, precision didn't matter. The irony was absolute. The Air Force's $1.5 billion bombsight delivered a $3 billion bomb that needed no bombsight at all. Carl Norden never learned his device had been used over Hiroshima. He died in 1965, believing his invention had reduced warfare's suffering through precision. The truth was more complex. Over 50,000 Norden bombsights were produced. They served through Korea and Vietnam. The last combat use occurred in 1967. Navy VO-67 Squadron dropping sensors on the Ho Chi Minh Trail. Post-war analysis revealed uncomfortable facts. In 1943, average bombing accuracy was 1,200 feet circular error. Only by 1945, with fighter escorts and lower altitudes, did accuracy improve to 60% within 1,000 feet. The Norden didn't fail. It worked exactly as designed. The doctrine failed. The assumption that precision bombing could win wars without fighter escorts. That technology alone could overcome human limitations under fire. The device now sits in museums. The Enola Gay's bombsight resides at the National Air and Space Museum in Washington. A monument to American engineering, to the belief that wars could be won cleanly, to the gap between laboratory perfection and combat chaos. The bombsight that promised to hit a pickle barrel from 4 miles up. The device that helped win a war. The machine that proved precision and accuracy are not the same thing. Every event, number, and name in this documentary has been verified through historical and documented sources.